Okay, so now we're gonna work on part 3, and the first thing we're gonna do for part 3 is we're actually gonna look at the BRODE function. So if you go to the bottom of your code, you'll see a template for the BRODE, and then so the inputs that you're gonna have for this function are gonna be all of your constants for a particular temperature, and then T and Y. You need T and Y because, as you recall, when you use the ODE solver, you need a function that is depending on T and Y. And in this case, these are all just like constants that you're gonna calculate with your Arrhenius equation. So then what we need to do first is understand that the only output is going to be your dy dt function, and then that it's going to be, so y itself is going to be divided, it's going to be a matrix with 5 columns. Each column is going to represent a different variable. So as you see here, the first column is going to be g, then the second one is going to be m, and the third one is going to be n, and then so forth and so on. So now we're looking at a matrix. Before, when we used to do ODEs, our output was a temperature vector and then a y vector. Now we're going to actually have a y matrix. Just need you guys to understand that. Now, the first thing that we're going to do is, in order to do the BRODE, we need to write all of the equations that we have in our PDF. So starting from all the mu's, we're going to type all of them down. So we're going to say mu1. You can call it whatever you want. So mu1 is going to be Vg, and then times G divided by Kg plus G. And like that, you're going to type all of them. So we start with mu1, but then we're going to do mu2, and then mu3, and then you're going to start with dg. So you go dg dt, and then that's equal to just negative mu 1 times x, and then like that you're gonna type dg dt, dm dt, dn dt, dx dt, and de dt. So far we're gonna have 3 mu's, mu1, mu2, mu3, and then dg, dm, and dn, and dx, de, dt. Okay? So then the last equation that you should have is your actual du dt or dy dt. So how you see it here is that we have the output is dy dt. So in a part of your code, there has to be a variable called dy dt, which is what is going to output. So why do we type all of the mu's and then all of the differential equations? Is because they're all going to be part of our dy dt equation. So the reason why we type the mu's is because the differential equations depend on the mu's. And then each differential equation is going to be a column of our dy dt. So then what we need to do is we make dy dt a matrix, and then we're going to make the first one be dg dt, then colon, semicolon, then dm dt, and then so on and so forth until you get to de dt. So you're going to have 1, 2, 3, 4, 5 columns in the dy dt corresponding to each one of your differential equations. So here I just typed like 2 as an example, but you're gonna have all of them typed here, and then this one goes at the end, and that's it for your BRODE function. So it's very easy. Now we go to part 3 to actually solve the problem, and so the first part is to actually make the function, which we have done. Now we have to solve the using ODE. So I changed it here. Your template says ODE 45. We're gonna instead use ODE 15s because it's gonna allow us to solve the problem a lot faster. So this problem that we're solving is considered a stiff problem, and for stiff ODE problems, Matlab has specific ODE functions that help you solve them faster. So then, since we're saying that this is going to be a 14 degrees C, the first thing that we have to do, of course, is to calculate all of our constants at that particular temperature. So we can just copy and paste our Arrhenius equation. And then instead of T, we're going to have 14. Now what this is going to do again is going to go to your Arrhenius function. It's going to type 1440 and it's going to calculate all of our constants. Again, we need all of these constants because they're also inputs for our beer ODE. Please don't forget that everything that's on the right inside the parenthesis are inputs for the equation that you're just creating, and everything that's on the left is the outputs. So before we had one input and then all of these outputs. Now we have all of these inputs and then just the one output. You might wonder why we have T and Y when T and Y they don't show up in any of our equations, and it's because if you remember, when you make an ODE, when you make a function for an ODE, you normally make it as an anonymous function that's depending on T and Y. So that's what we have to do now. Right now we have a function which is VROD that depends on too many things, and Matlab only takes functions for the ODE that depends on T and Y. But now these are all just constants, so now we can go ahead and create a function. We can just call it f, and then it's going to be an anonymous function that is going to depend on T and Y, which are the requirements for an ODE anonymous function. Now, this is just going to be your ODE equation. So what you can do is just go ahead and copy and paste your beer ODE. And again, you might wonder why we have to do this if we're just going to say it's the same thing. We're basically saying F is equal to beer ODE. But again, now that we have all of these constants, our beer ODE is, all of these are going to be constants, and it's literally just going to depend on T and Y. However, we cannot use this beer ODE using the ODE solver because the function can only depend on two parameters, in this case T and Y. So that's why we have to make a new function just for Matlab to use for the ODE. Once we have that function, the only thing that we have to do now is to, as we have done before, use the ODE solver using that function. So if you don't remember, when you're going to solve an ODE, you need to create first a matrix that has first your time vector and then your output, and then we're going to use the ODE. So in this case, ODE 15s, you do the exact same thing you did for ODE 45. It's just now it's 15s, and now we open parentheses. So I'm not going to fill this up. I'm going to let that up to you, but I'm going to show you what goes inside. So first is the ODE function, which in our case is f. Then it goes the t-span, which in your PDF it tells you from 0 to 200 or 0 to 100. I'm not sure, so you're going to make that a t-span. Then you need your y naught, and then your options. And now you may ask yourself, like, why is your y naught? Well, now in order to do this problem, you actually have to create a vector of your initial values. Before, we used to just make one initial value. Now we need a vector of initial values. And in your sheet, they're given to you, and they tell you that your initial values are 60, 160, 80, and then so on. So we need to separate them by semicolons because each of these initial values is an initial value for each one of our differential equations. So 60 is going to be the initial value for the dGdt. Then we have 160 is going to be the initial value for our, so if we type them in order, then it's going to be for the dmdt, and then so on. So they all have to be in that same order that they're given to you. So if we go back here, then we're going to have the f, that's the function we created, the t-span, which is 0 to 100 and 0 to 200, y naught, which is just your y naught, and then options. So for this particular problem, we actually do want to set options.